friends. The speaker is Håkon Gylterud, and he will speak about non-well-founded sets in homotopy type theory.
Thank you. So what we're actually going to do is that we're going to construct a particular model of non-well-founded sets in homotopy type theory. So to give a quick summary of what we're going to say, we're going to have a presentation of previous models of set theory in type theory. And then we're going to see like where is the hole for this model, which we're going to construct here. And then we're going to discuss a bit about power sets and images. And in particular, we're going to have an additional assumption on our universe in order to construct the model. And then we will actually construct the model. And then we'll discuss a bit about what axioms are satisfied by the model. And I should mention that this is joint work with Elizabeth Bonnevier. And this talk will be rather short on details. So if you want the details of this construction, you should look at the preprint, but you shouldn't look at the preprint today. You should look at it tomorrow when Archive has updated it to the best version. There's also Agda code, but that's more in progress. So quite a number of the axioms have been proven, but the model construction itself has not come very far in the Agda code, but that will improve hopefully soon. So non-well-founded set theory. So the axiom of foundation says that all sets are accessible, or rather that you can prove stuff about all sets by doing induction on epsilon. So the epsilon relation is well-founded. And this axiom is quite the odd one out if you look at the rest of the set theoretic axioms, because it says that some kinds of sets can't exist. There can't be non-well-founded sets. While the rest of the axioms in set theory, they say what kind of sets we can construct. So they say there are pairs, there are unions, there are exponentials, and so on. So the axiom of foundation is sort of the odd one out, and removing it leaves open the question, like, what are these non-well-founded sets? And that is what Axel's anti-foundation axiom answers, namely that it says that whenever you have a relation or directed graph, there are sets which you can decorate the graph with, such that the edges of the graph specify the epsilon relation, the element relation between these sets. So, for example, the Quine atom, which is specified by being the singleton of itself, so it's this sort of canonical example of a non-well-founded set, is specified by the graph which has a single node and an edge from that node to itself. And even adding this one non-well-founded sets has some implications about how we do mathematics, or how mathematics is formulated. For instance, if you look at the natural numbers, the usual way we formulate the existence of natural numbers is to say that the natural numbers are the unique set which contains 0, and where every set is, where every element is the successor of some set, or 0. But this Quine atom, it is its own successor. So if you take the natural numbers, the usual ones, and you add the Quine atom to it, then you get another set which also satisfies this axiom, because the Quine atom is also a successor of some element in the set, namely itself. So if you want the usual natural numbers, you have to specify that you want the accessible set. So that you get only the natural numbers you want and not something including this Quine atom. That's a bit about non-well-founded sets. Now we're going to talk about models of type theory, of set theory in type theory. And I've chosen a few models here, which you can see. And the first one is Axel's model from 1978. And then there's Lindström's model from 89, and then there's the V from the Hot book. And if we look at them, they are either initial algebras or terminal coalgebra constructions. So this is clear in the case of Axel's model, where the underlying type of the model is a W type, and is the fixed point of the operation, which you see on the left-hand side here, which takes a type to the sigma over all A and U, A arrow X. And so an element of Axel's V is essentially an a small type, and a map into V itself. So you can think of that as A being the elements of the set, which it represents, and this function pointing out which sets are represented by each element. Now, there's nothing saying that this can be, this has to give a new set for each element. So one set can be pointed out any number of times. So Axel has to do this setoid construction where he defines an equivalence relation, which sort of blurs out that distinction. And that's also what Lindström does, except that she takes the M type, so the dual construction to Axel, and shows that it is also a model of set theory, but satisfies anti-foundation. So there already is a model of anti-foundation in the usual set theory. But for neither of these models, the identity type is the right notion of equality, and that's sort of fixed in the HoTT book, where you have this the ability to make hits, and you take the actual quotient of the relation, and then you get something which is a fixed point for this operation, where A has to be embedded into X. So you get that an element of V is exactly something from the universe and an embedding into the universe of sets. And you actually can do this without hits as well. You can just identify inductively the set-like elements here. There's canonical representations of the equivalence classes up here. And what we are going to do is to take the dual construction of that and construct the terminal coalgebra of this operation. In all cases, the way we construct the model is the same. We say that elementhood is defined by inverse images like this. So our model will be the greatest fixed point of this kind of small power type operation. So this small power type operation takes any type and returns the type of U small subtypes of X. And so that's a bit different from the usual power set operation, if you imagine it as functions into some set of propositions. So it will be different from, this is different from taking functions from X into U small propositions, for instance, but these are all the U small subsets. And let's see. This thing is also a set, which is quite easy to check. And then the question is, because we want to construct the terminal coalgebra of this, we want to talk about coalgebra homomorphisms, and for coalgebra homomorphisms to make sense, we need that P is in some sense functorial, so that we can lift these things. At least for the kind of types we care about. So we know that P is going to be functorial for small sets, because taking images is no problem inside small sets, but lifting functions from general types, it's not so clear that we can do that out of the box. And then in order to do that, we need to discuss a bit images of small types into larger ones. That's the next point here. So this is the usual diagram for image factorization. So you have some A and you have some function F, which goes from A into X, and then you can factor it through a surjection and an embedding. And the question is here, what is the size of the image, given that we know something about the size of A and the size of X? So first of all, if A and X are both in U, then it's quite clear that we can construct the image because we can characterize the image as a subset of X. It's all the elements of X for which there merely exists an A such that F of that A is equal to the X we started with. But if A is small and X is large, it's not so easy. Even though the image is has a surjection from A. There's no principle which tells that if we have a surjection from something, then it's also small. And I'm not sure that would be constructively valid or predictively valid. But if we think about the image as a higher groupoid, as a higher groupoid structure, then we can imagine that the fact that there's a surjection here sort of says that the objects of the image are exactly like the objects of A, and then the inclusion here says that the paths in the groupoid are exactly like the paths for the corresponding elements in X here. So the principle we want to arrive at is that if A is small and X is locally small, that all the identity types are essentially small, that they are equivalent to things in the universe, then it should be somehow okay to assume that the image is also U small. So that's the principle. And that's not going to hold for any universe. So we have to add it as an assumption because it allows us to glue together groupoids in a way which we can't do for any universe. But at least to me, that makes a lot of constructive sense that you can glue to, if the HOM sets are small and all the objects form a small set, then it makes sense that you can glue together a small groupoid from that. Okay, and this then allows us to establish functoriality of this PU, because if you have an element of Px, so that's an A in the universe and some inclusion into X, and you have an F from X to Y, well, then you can compose those two and you get just a function into X, but you can force that into making an inclusion by taking the image. And if then Y is locally small, which will be in the cases we consider, then this image would also be small. Okay. So back to the model of non-well-founded sets. So the way we construct the model is that we start with the M type, the type which Lindström used, and we call that M infinity. And it's the terminal coalgebra for the operation, which doesn't include the embedding part, but allows any function. And then we want to sort of carve out from that terminal coalgebra, we want to carve out our terminal coalgebra, where all the functions are actually embeddings. So for the inductive case, that was easy, because to make the predicate that something is iteratively a set, you can define that by induction. So in the case of doing this for the iterative sets, this is straightforward because defining a function out of an inductive type is easy. Defining a function out of a co-inductive type is not so easy. So I was for some time stumped on how to do this. But the solution I found was that we could, instead of defining a predicate, we will define an endofunction on this larger type, which at each level forces the injectivity. So, and then we will let the V which we're looking for, which we have called here V0 infinity. And so the 0 here indicates its level, so it's a set, and the infinity is like in the co-natural numbers, that it includes also the infinite trees, so to say. Okay, so we'll define an endofunctor, and the image of that will be the thing we're looking for. And the way to define this endofunction is by taking images. So we're going to use that axiom, which allows us to take small images of things into this M, because this M is large type, but it is locally small. So it's okay to take images of small types into that if we agree to the assumption. So in order for us to define a function from M into M, well, we're going to do that co-recursively. So we're going to get the square on top here is a coalgebra homomorphism, and it's into the coalgebra which we're given for the M type. And it's done by first using the usual deconstructor for M, and then taking the image so that we get something here which is actually injective. And then, so that's another coalgebra structure for M. And then that coalgebra structure induces a map into the terminal one, and we get a function sigma here, co-recursively defined. And then this V is just the image, which we factor through here. And because of the square on top here, we know that if we start in V and I go up, look at its deconstruction, we will end up with something which, first of all, is injective, and where all the other things we can observe from V also lie in V. So that makes V a coalgebra for the small power type functor. Okay, so I'll sum up by talking about what axioms are satisfied. So first of all, a lot of the axioms, well, all but the anti-foundation axiom can be shown for any fixed point of PU. So they can be shown uniformly for either the initial one or the terminal one. You can take any fixed point. And from there, it follows that extensionality holds. You can do replacement, restricted separation. You can construct the empty set, pairing, union, exponentiation, and natural numbers. All these do not actually care about the all the levels of the hierarchy. They only work at some limited level. So they can be shown by just assuming that it's a fixed point that you can go back and forth between subsets and elements. But if you look at this one in particular, then you can show that it satisfies anti-foundation, and that's actually quite straightforward because of the way it was defined and the way we show that it was a coalgebra. So that concludes what I wanted to say. So please let me know if you have any questions.
Yes, so I unmuted myself. So let's thank you first. And so are there any questions in this worldwide audience? Yes, Mark.
Oops.
Yes.
Me again. So Axel has a regularity property also for his sets, and I think it also holds for the non-well-founded sets. So have you thought about proving that?
No, I haven't.
Yeah, you have to go look in. Axel had a series of 3 papers, and you have to go look in, I don't know, the second or third one to see how the regularity axiom he has. Yeah. I did a similar thing, formalizing all that stuff in NuPrel using co-W types, and the regularity property worked for me. But I'm using the setoid idea.
So there are some differences between the setoid model and this. Yeah. For instance, in the setoid model, it's easy to show subset collection, but that's not possible to show for these models where we actually take the quotient in type theory. Yeah. So we only get exponentiation.
using the setoid way, I had a very hard time, proving, what the equivalence relation was on the non-well-founded things, because it had to be, by simulation, which is some kind of a game. It's like a strategy, a winning strategy for a certain game, and it all worked out, but it was hard work. So if
Yeah.
All right.
Can I ask a question?
Go ahead.
So you mentioned this assumption about closure under images
Yeah.
into locally small types. Are you aware of Egbert Reika's work on that?
No, but I would be happy to get a pointer to that.
Yeah, so
Yeah.
he's got a paper called The Join Construction, where he proves that that's true. Given, I think, push-outs. He can construct the image as an object of the same universe. So I think it answers exactly the assumption you need.
Okay, that's cool. The joint construction. Okay, I'll check that out.
So well, maybe we should thank you again, and maybe one of the organizers